Good evening, everyone. How is everyone this evening? I'm also good, thank you. So let's wait another minute or two and see who else is joining us for this lecture. I'm also well, thank you. So while we're waiting another minute or two, is there anything you guys want to share with the class, something interesting you read or seen? See, before you start, sir, I saw something on the net that bacteria, viruses, and worms that have been frozen for thousands of years are starting to be unfrozen due to global warming, and scientists fear that they may prove to be lethal to the human race as they are not adjusted to living with humans like flu and other diseases. I just thought could be a similar situation happen on Mars if you try to unfreeze the water there and use it as assuming it as microbial life that is frozen. Yes, that is exactly a possibility. So these worms and bacteria that I found frozen. One thing is now that was frozen for a long time, and now as they become unfrozen and is becoming back to life, we don't have any idea what impact it will have on other life. Will it cause diseases? Will it start dominating the food chain? Because um, didn't have any natural predators or natural protection the last couple of 100,000 years. So the same thing could happen on another planet, another moon as well. And therefore, there's a initiative. Each government is supposed to have a position called a planetary protection officer. So not many countries has adopted that yet. The US has a planetary protection officer. Russia has one. China has one. Um, all of the European countries has. Canada has. So basically, every country that has a space program has a planetary protection officer. The planetary protection officer is on the same levels, for example, as in the US as the director of national security, director of the FBI, director of the CIA. And we have one that's actually a good idea. I don't know if South Africa has a planetary protection officer, but the position in the US was created back in the 60s with the Apollo missions. So for example, when the Apollo astronauts came back to Earth, they were put in quarantine to make sure they didn't bring anything dangerous from the moon with them. So it's the Planetary Protection Officer's duty to investigate these different scenarios and have contingency plans in place on how to deal with it. You see, so, oh, I didn't know Neil deGrasse Tyson has a TikTok page. I usually follow Neil deGrasse Tyson on um, Facebook and Twitter. Pleasure. So let's start with tonight's lecture. So something that I can start from the shoot, like I say, shoot from the hip with, and a fact I can bombard you with before we start. Neptune wasn't discovered by observations. Neptune is the only planet that was predicted by math. By making use of Kepler's laws and Newton's laws and crude mathematical models, it was predicted that a ninth planet must exist in a certain place, and they calculated where Neptune was supposed to be. And when they pointed their telescopes to That spot they found at Neptune. So through a telescope on Earth, Neptune looks like a tiny blue dot with no visible cloud features. In 1989, Voyager 2 flew past and revealed most of what we know today about Neptune. Almost exactly the same size as Uranus, Neptune has a smaller interior. Model calculations predict that a small core of heavy elements lies within a slushy mantle of water, ices, and rocky materials below a hydrogen-rich atmosphere. Yet Neptune looks quite different on the outside from Uranus. Neptune is dramatically blue and has active cloud formations. Neptune's dark blue tint is caused by its atmospheric composition of 1.5 times more methane than Uranus. Methane absorbs red photons better than blue and scatters blue photons better than red, giving Neptune a blue color and Uranus a green-blue color. Atmospheric circulation on Neptune is much more dramatic than on Uranus. When Voyager 2 flew by Neptune in 1989, the largest feature was the Great Dark Spot. Roughly the size of Earth, the spot seemed to be an atmospheric circulation pattern like Jupiter's Great Red Spot. Smaller spots were visible in Neptune's atmosphere, and photos showed they were circulating like hurricanes. Most recently, the Hubble Space Telescope has photographed Neptune and found the Great Dark Spot is gone, and new cloud formations has appeared. And we can look at the figure now. Evidently, weather patterns on Neptune are very changeable. So here we can see the Great Dark Spot. So here we can see different images of Neptune, so in 96, 98, 2002, and this is the flyby of Voyager 2. The atmospheric activity on Neptune is apparently driven by heat flowing from the interior plus some contributions by dim sunlight 30 AU from the sun. The heat causes convection in the atmosphere, which the rapid rotation of a planet converts into high-speed winds. High-level white clouds are methane, ice crystals, and rotating storms visible as spots. Neptune may have more activity than Uranus because it has more heat flowing out of its interior, for reasons that are unclear. Like Uranus, Neptune has a highly inclined magnetic field that must be linked to circulation in the interior. In both cases, astronomers suspect that ammonia dissolved in a liquid water mantle makes the mantle a good electrical conductor, and that convection in the water, coupled with rotation of the planet, drives a dynamo and generates the magnetic field. Neptune has 2 moons that were discovered from Earth before Voyager 2 flew past in 1989. Voyager discovered 6 more very small moons. Since then, a few more small moons have been found by astronomers using Earth-based telescopes. The 2 largest moons have peculiar orbits. Nereid, about a tenth of the size of Earth's moon, follows a large elliptical orbit, taking nearly an Earth year to circle Neptune once, and Triton, almost 80% of the size of Earth's moon, orbits Neptune retrograde, meaning backwards. These odd orbits suggest that a system was disturbed long ago in an interaction with some other body, such as a massive planetesimal. With a surface temperature of about 36 Kelvin, this is wrong, so that seems as a typo I made. This should be minus 150 something Celsius. Triton has an atmosphere of nitrogen and methane about 10 to the 5 times less than Earth's. A significant part of Triton is ice, and deposits of nitrogen frost were visible in the southern pole, which at the time Voyager 2 flew past had been turned towards sunlight for 30 years. Thank you, Mr. Silva. The nitrogen frost appears to be vaporizing the sunlight and is probably freezing in the darkness at Triton's north pole. So here we can see in image A, visible wavelength images of Neptune's moon Triton. Triton's southern pole cap is formed of hydrogen gas. No dark smudges caused by organic compounds sprayed from the nitrogen geysers, and the absence of craters. Then in image B, these round basins on Triton appear to have been repeatedly flooded by liquid from the interior. Many features on Triton suggest it has had an active past. It has a few craters on its surface, but it does have long faults that appear to have formed when the icy crust broke. Some approximately round basins, about 400 kilometers diameter, appear to have been flooded time after time by liquids from the interior. Analysis of dark smudges visible in the southern polar cap reveals that these are deposits produced when liquid nitrogen in a crust warmed by the sun erupts through vents and spews up to 8 kilometers high into the atmosphere. Methane in a gas is converted by solar ultraviolet radiation into dark compounds that fall back, leaving black smudges. By counting the craters on Triton, planetary scientists conclude that the surface has been active as recently as 1 million years ago and may still be active. The energy source for Triton's geyser activity could come from radioactive decay. The moon is 2/3 rock, and although such a small world would not be able to generate sufficient radioactive decay to keep molten rock flowing to its surface, frigid Triton may be the site of water-ammonia volcanism. A mixture of water and ammonia could melt at very low temperatures and erupt to resurface parts of the moon. Then we come to Neptune's rings. Neptune's rings are faint and very hard to detect from Earth, but they illustrate some interesting principles of comparative planetology. Comparing the rings of Neptune with those on Uranus, notice 2 additional points. Neptune's rings, named after the astronomers involved in the discovery of the planet, are similar to those of Uranus but contain more small dust particles. Also, Neptune's rings show another way that moons can interact with rings. One of Neptune's moons is producing short arcs in the outermost ring. Neptune's rings resemble the rings of Uranus, Saturn, and Jupiter in one important way. As you've already learned, these rings can't be primordial. That is, they can't have lasted since the formation of the planets. Planetary rings are constantly being remade. Neptune must have formed much as Uranus did, growing slowly and never becoming massive enough to trap large amounts of hydrogen and helium. It developed a core of heavy elements, a mantle of slushy ices and rock, and deep hydrogen-rich atmosphere. Neptune's internal heat may be generated partly by radioactive decay in its core and partly by dense material sinking inward. Laboratory experiments show that at the temperatures and pressures expected deep in the atmospheres of Neptune and Uranus, methane can decompose, and released carbon might form diamond crystals, perhaps as large as pebbles. A continuous flow of diamonds falling into a planet's interior would release gravitational energy and help warm the planet. This process may be the source of some of Neptune's internal heat, but a lack of internal heat in Uranus remains a puzzle. The possibility of a planet-wide hailstorm of diamonds serves to remind you that other worlds are truly and unearthly and may harbor things you can hardly imagine. The heat flowing outward towards Neptune's surface can drive convection, produce a magnetic field, and help create atmospheric circulation. The moons of Neptune suggest some cataclysmic encounter long ago that put Nereid into a long period elliptical orbit and Triton into a retrograde orbit. You've seen evidence of major impacts throughout the solar system, so such interactions may have been fairly common. Certainly, impacts on satellites could provide the debris that is trapped among the smaller moons to form the rings. Out on the edge of the solar system orbits a family of small icy worlds. Pluto was the first to be discovered in 1930, but modern telescopes have found more. You may have learned in school that there are 9 planets in our solar system, but in 2008, the International Astronomy Union voted to remove Pluto from the list of planets and reclassify it as a dwarf planet. Pluto is a very small icy world. It isn't Jovian and it isn't terrestrial. Its orbit is highly inclined and elliptical, enough that Pluto actually comes closer to the Sun than Neptune at times. To understand Pluto's status, you can use comparative planetology to analyze Pluto and then compare it with its neighbors. So according to me, Pluto should have been kept a planet just purely out of tradition, but now it's been reclassified as a dwarf planet. Yes, Mr. Levuyo.
Good evening, sir.
How are you?
I'm okay, thank you, sir. And yourself?
I'm well, thank you.
So question, sir. So, because Pluto's orbit is on an incline, sir, over time, sir, because of the conservation of momentum, sir, angular momentum, sir, will it eventually also become like have a flat orbit?
That is a really good question. So due to angular momentum, it will remain in the orbit as it is and will continue on that way. So during the formation of our solar system, something happened that puts Pluto on such a weird orbit.
But then, sir, like because our solar system, I mean not our solar system, so the galaxy sort of started in like a spherical sort of ball of plasma and gas. So wouldn't the same thing sort of happen to Pluto, because like everything eventually becomes flat?
Yes, I'm looking for an image I want to show you that will perhaps put this in better perspective. Let's quickly see if I can find what I'm looking for. Yes, this will work. So I'm quickly going to upload this file so I can show this to you guys. Where is it now? So this image is a crude estimation of what is happening in the orbit. So we'll see all of our planets, yes, the terrestrial worlds, are in the same disk. If we look at the Jovian worlds, they are all in the same disk. Instead of, you can see Uranus is also in a bit weird orbit, and you can see Pluto is in a orbit as well. So it will remain in, let me get this out, in this orbit. So as we have already learned, we can find objects looking at galaxies as well that orbits the galaxies in other eccentric orbits, but I will keep that orbit, although most of the other planets in the solar system will be in this line. It all depends on what happened during the planet's formation and how it ended up today.
So is it possible for like all planets to have like different sort of orbits and not all of them are on the same plane?
Yes, that could happen. So we have observed a few other solar systems there where planets have eccentric orbits. Because remember, everything comes down to Kepler's laws. So in Kepler's laws, we need our central body that is the Sun, and then depending on how the object formed, it's in a orbit around the Sun. And here is our planet, so it will sweep these areas in equal amount of time, but we can even have our central orbit with a object that's totally in a different orbit. But if you do the math on this, it doesn't matter if your orbit is inclined in this way or inclined in that way, it's still orbiting a central body, and a central body is keeping everything in place.
Thank you, sir.
Pleasure. So let me go back to the slides. So we were almost at the end of the slides. So I'm going to ask you, if Pluto is not terrestrial or Jovian, it is classified as a dwarf planet. So we will learn now what is a dwarf planet. So Pluto is very difficult to observe from Earth. Its diameter is 2,370 kilometers, smaller than, so that means it's smaller than Australia and only 2/3 the diameter of Earth's moon. In Earth-based telescopes, Pluto never looks like more than a faint point of light. And even in Hubble Space Telescope images, it shows little detail. Orbiting so far from the Sun, Pluto is cold enough to freeze most compounds you think of as gases. And spectroscopic observations have found evidence of nitrogen and methane ices on its surface. Pluto has a thin atmosphere of nitrogen and carbon monoxide with small amounts of methane. Pluto has 5 known moons. 4 are quite small, but Charon is relatively large, with half of Pluto's diameter. Charon orbits Pluto in an orbit inclined at 180 degrees to the plane of Pluto's orbit around the Sun, which means Charon motion is retrograde. Pluto and Charon are tightly locked, facing each other, so Pluto's axis of rotation is inclined at the same large angle to its orbit, such that its rotation is also retrograde. Knowing Charon's orbital period of 6.4 days and orbit semi-major axis of 19,600 km allows you to use Kepler's third law to calculate that the total mass of the system is only about 0.0024 Earth mass. Most of that mass is Pluto, which has about 9 times the mass of Charon. Knowing the diameters and masses of Pluto and Charon allows determination that Pluto densities are respectively 1.9 and 1.7 grams per cubic centimeters. That indicates that both Pluto and Charon must contain about 30 to 40% ice and 60 to 70% rock. The New Horizons spacecraft flew past Pluto in July 2015. Radioing back impressive images and other measurements. Close-up pictures show mountains up to 3.5 kilometers high. Methane and nitrogen ice would not be strong enough to stand that tall, so planetary scientists concluded that the mountains must be made of water ice that could be rock hard at Pluto's temperature. The lack of craters on and near those mountains indicated this peculiar landscape is very young, no older than 100 million years. One of the youngest surfaces observed in the solar system. Pluto has been active geologically recently, which means that heat must be flowing outward, although planetary scientists wonder what an internal heat source could be. Charon's orbit is perfectly circular, so tidal heating is not the explanation. Radioactive decay would seem to be the only plausible alternative, although that heat source should also have faded long ago. One planetary scientist on New Horizons team remarked, "This may cause us to rethink what powers geological activity on many other icy worlds." Pluto turns out to be a world full of surprises. So what defines a planet? To understand why Pluto is no longer considered a planet, you should recall what you have already learned about the Kuiper Belt in chapter 15. Since 1992, astronomers have discovered more than 1,000 icy bodies orbiting beyond Neptune. This may be seen as many as 100 million Kuiper Belt objects larger than 1 kilometer in diameter. They are understood to be icy planetesimals left over from the outer solar nebula. Some of the Kuiper Belt objects are quite large, and one, Eris, has about the same size as Pluto but is 27% more massive. 3 other Kuiper Belt objects found so far, Sedena, Quaoar, and Orcus, are half the size of Pluto or larger. Eris, Quaoar, and Orcus are known to have moons of their own. In that way, they resemble Pluto and its family of moons. A bit of comparative planetology shows that Pluto is not related to the Jovian or terrestrial planets. It's obviously a member of a newfound family of worlds that orbit beyond Neptune. These bodies must have formed at about the same time as the 8 classical planets of the solar system, but it did not grow massive enough to clear the orbital zones of remnant planetesimals and consequently remain embedded among a swarm of other objects in the Kuiper Belt. The International Astronomy Union's criteria for the full planet status is that an object must be large enough that it has gravity. Its gravity has pulled it into a spherical shape. So remember, this is a good question also for the exam. Spherical shape, and also large enough to dominate and gravitationally clear its orbital region of most or all objects over a span of billions of years. Eris and Pluto, to the largest objects found so far in the Kuiper Belt, and Ceres, the largest object in the asteroid belt, are too small to clear the orbital zones of other objects and therefore do not meet the standard for being called planets. On the other hand, all 3 are large enough to be spherical, so they are the prototypes of a new class of objects defined by the IAU as dwarf planets. So now we could start to look at Pluto and the Plutinos. So no, this section is not about the 1950 rock band. It is about the history of the outer solar system, and it will take you back 4.6 billion years to watch the planets form. More than 100 of the Kuiper Belt objects are caught with Pluto in a 3:2 resonance with Neptune. That is, they orbit the Sun twice, while Neptune orbits 3 times. The subject of Kuiper Belt objects has been named Plutinos. Plutinos formed in the outer solar nebula, but how did they get caught in resonance with Neptune? As you learned earlier, some models of the formation of planets suggest that Uranus and Neptune may have migrated outward early in the solar system's history. As Neptune moved further from the Sun, its orbital resonance could have swept up small objects, like a kind of planetary snowplow. The Plutinos are caught in this 3:2 resonance, and other Kuiper Belt objects are caught in other resonances. Evidence appeared to support those models that predict that Uranus and Neptune migrated outward. The migration of the outer planets would have dramatically upset the motion of some of the Kuiper Belt objects, and some could have been thrown inward where they could interact with the Jovian planets. Some of those objects may have been captured as moons, and astronomers wonder if moons such as Neptune's Triton could have started life as Kuiper Belt objects. Other objects may have hit bodies in the inner solar system and caused the late heavy bombardment episode, especially evident on the surface of Earth's moon. The small frozen worlds on the fringes of the solar system may hold clues to the formation of the planets 4.6 billion years ago and the subsequent history of Earth. So, this was our lecture on the planets. So before we start with aliens, there's one other thing we haven't discussed yet. And you guys know what that could be. Yes, Mr. Levuyo.
So I was also going to say asteroids.
You guys are correct. So the only thing we haven't discussed yet are asteroids and comets. So this is the second last set of lecture slides before our last lecture that will be on alien life. So now we're going to look at meteorites, asteroids, and comets. So, have any one of you ever observed or seen a asteroid, meteoroid, or comet before? Yes, Halley's Comet. I'm also waiting for Halley's Comet. So the best way, if you've ever been in a dark place and you look up in the night sky and you see a small bright object moving across the sky, that is a meteorite entering the Earth's atmosphere that you see. And usually, if you are in a city and you look upwards, you should be able to see between 2 and 5 meteorites per hour. In darker skies, it will be much more. Right about August, we move through the tail of a comet and we get meteor showers. And then usually you can see between 15 to 30 per hour. So this is typical how a meteorite will look like. So usually a meteorite, the telltale that a meteorite has hit the ground and survived and not burning out in the atmosphere is most of these meteorites consists out of iron. So how many end up hitting Earth? So hitting Earth can be from a few centimeters in diameter to a few meters. So let me just pull up the stats. Mm, So usually the latest statistics are, so right now at Hartebeespoort, we are setting up a meteorite tracking system. So currently there's about 17 hit Earth per day, more or less. So, so on average, it's about 500 meteorites per year. Sounds cutting, sometimes you hear them, sometimes not, and the color in which they burn is usually due to decomposition. So here are some of the biggest asteroids currently in our solar system. So here you can see Rosetta. There was a probe that landed on Rosetta not too long ago. And you can see it's 132 by 101 by 76 kilometers in size. And here you can see Eros. There's also a popular one, and a few other. And this is usually how a comet will look like with the tail we are seeing. So in chapter 15, you began your study of planetary astronomy by considering evidence about how our solar system formed. In the following three chapters that followed, you surveyed the planets and found more clues about the origin of the solar system, but also learned that most traces of the early histories of the planets have been erased by geological activity or other processes. Now you can study smaller, less altered objects that tell more about the era of planet building. Asteroids and comets are unevolved objects, leftover planet construction bricks. You will find them much as they were when they formed 4.6 billion years ago. Meteors and meteorites are fragments of comets and asteroids that arrive at Earth and can give you a close look at those ancient planetesimals. Question, sir, do you think sir, do you think where we are currently is asteroid mining realistic or doable? Yes. And that is something we are coming up in this, I can't remember my slides, but in this lecture or in our last lecture. So as you explore, you will find answers to 4 important questions. Where do meteors and meteorites come from? What are asteroids? What are comets? And what happens when asteroids and comets hit Earth and other planets? One afternoon, while Mrs. E. Hewlett Hodges of, how do you pronounce that? Sylacauga, Alabama, lay napping on a living room couch, an explosion and a sharp pain jolted her awake. Analysis of the brick-sized rock that smashed through the ceiling and bruised the left leg showed it was a meteorite. Miss Hodges is the only person known to have been injured by a meteorite. Coincidentally, she lived right across the street from a Comet Drive-in theater. That is ironic. Meteorites arrive from space all over the Earth every day. Although not as spectacularly as the one that struck Miss Hodges, you will learn in this chapter that meteorites are fragments of asteroids, and that asteroids, as well as their icy cousins the comet, carry precious clues about conditions in the solar nebula from which the sun and planets formed. Because you cannot easily visit comets and asteroids, you can begin by learning about pieces of those bodies that come to you. You learned some things about meteorites in chapter 15, section 2, when you studied evidence for the age of the solar system. There you saw that the solar system includes small particles called meteorites. Some of them collide with Earth's atmosphere at speeds of 10 to 70 kilometers per second. Friction with air heats the meteorites enough so that they glow, and you see them vaporize as streaks across the night sky. Those streaks are called meteors or shooting stars. If a meteorite is big enough and holds together well enough, it can survive its plunge through the atmosphere and reach Earth's surface. One of the objects strikes Earth's surface is called a meteorite, being Greek root for rock. As you will learn later in this chapter, the largest of those objects can blast out craters on Earth's atmosphere, but such big impacts are extremely rare. The great majority of meteorites are too small to form craters. What can meteorites and meteors tell you about the origin of the solar system? To answer that question, you can consider their composition and their orbit. So, for you guys that's interested, if you go on to sites such as eBay, people pay a crap load of money for a meteorite. One of the best places to look for meteorites turns out to be certain parts of Antarctica. The nearest Earth rocks are buried under miles of ice, so any rock you find there must have fallen from space. The slow flow of the Antarctic ice cap toward the ocean concentrates meteorites in areas where the moving ice runs into mountain barriers, slows down and evaporates. Teams of scientists travel to Antarctica and ride snowmobiles in systematic sweeps across the ice each southern hemisphere summer to recover meteorites. After 25 years of work, more than half of the 40,000 meteorites in humanity's possession are from Antarctica. So here we can see braving bitter cold and high winds. Teams of scientists riding snowmobiles search for meteorites that fell long ago in Antarctica and are exposed as the ice evaporates. When a meteorite is found, it is photographed where it lies, assigned a number, and placed in an airtight bag. Thousands of meteorites have been collected in this way, including rare meteorites from the Moon and Mars. Meteorites can be divided into three broad composition categories. Iron meteorites are solid chunks of iron and nickel. Stony iron meteorites are mixtures of iron and stone. Stony meteorites are silicate masses that resemble earth rocks. And carbonaceous chondrites are a special type of stony objects. So here we can see the iron meteorites, silicated, stony iron melted cut, stony meteorites. And here we can see them in relation to one another. The most common one I've stumbled across is the iron meteorites. Iron meteorites make up only 6% of the meteorites witnessed falling from the sky. So you can estimate that only about 6% of meteorites traveling through space near Earth have iron composition. Then you might wonder, why do iron meteorites make up 66% of meteorites found on the ground? Because iron meteorites don't look like ordinary rocks. They are easy to recognize because they are heavy, dense lumps of metal. If you trip over one on a hike, you're more likely to recognize it as something odd. Carry it home and show it to your local museum. Also, some stony meteorites deteriorate rapidly when exposed to weather. Irons are made of stronger material and generally survive longer. The recognizability and durability of iron meteorites means there is a selection effect that makes it more likely they will be found than other types of meteorites. So I don't know if you guys remember, but I think back in 2019 or 2018, a meteorite traveled over South Africa. So they asked people to submit their CCTV footage or any footage they have of the meteorite. So by making use of the footages, the trajectory of the meteorite was calculated, and it was actually found in Botswana. So yes, we're looking at a comment, Mr. Sage. Yes, 3 million for a meteorite. I know, those guys, they are ridiculously expensive. And yes, they are just small pieces of iron. When iron meteorites are sliced open, polished and etched with acid, they reveal regular bands called Whitman-Staton patterns, caused by alloys of iron and nickel that formed crystals as the molten metal cooled and solidified. The size and shape of the bands indicate the molten metal could vary slowly, indicating a location inside bodies at least 30 kilometers in diameter. In comparison, a small lump of molten metal exposed in space would cool in just a few hours. On the other hand, the iron meteorites do not show effects of the very high pressures that would exist deep inside a planet. Evidently, iron meteorite material formed in the cooling interiors of planetesimal-sized objects, smaller than planets. This is one important clue to the origin of meteorites. In contrast to irons and stony meteorites are common among meteorites seen falling to Earth. Although there are many different types of stony meteorites, you can classify them into two main categories depending on their physical properties and chemical content: chondrites and achondrites. Chondrites, like dark gray, granular rock. In general, chondrites contain some volatiles, including water and organic compounds. A few chondrites evidently formed in the presence of liquid water. Most types of chondrites also contain chondrules, small round bits of glassy rock only a few millimeters across. To be glassy rather than crystalline, the chondrules must have cooled from the molten state quickly within a few hours. One hypothesis is that chondrules are bits of matter from the inner part of the solar nebula near the Sun that were blown outward by winds or jets to cooler part of the nebula where they condensed and were later incorporated into larger rocks. Another hypothesis is that the chondrules were once solid bits of matter that were melted by shock waves spreading through the solar nebula and then re-solidified. Among the chondrites, the carbonaceous chondrites are a rare but quite important subtype. These dark grey rocky meteorites are especially rich in water, other volatiles and organic compounds. The substances all would have been lost if the meteoroid had been heated even to room temperature. Many carbonaceous chondrites also contain small irregular inclusions rich in calcium, aluminium, and titanium, called CIAs, for calcium aluminium rich inclusions. These bits of matter are highly refractory, that is, they vaporize or condense only at very high temperatures. If you could scoop out a portion of the sun's photosphere and cool it, the first particles to solidify would have the chemical composition of CIAs. As the temperature fell, other materials would become solid in accord with the condensation sequence described in chapter 15. When a cooling blob of solar composition material finally reached room temperature, you would find that almost all of the hydrogen, helium, and some other gases, such as argon and neon, had escaped, and that the remaining lump would have almost exactly the same overall chemical composition as the main mass of carbonaceous chondrite. Carbonaceous chondrite meteorites are evidently very old samples of the solar nebula, confirmed by the fact that CIAs have radioactive ages equal to the oldest of any other solar system material. The chondrites show properties ranging from carbonaceous chondrites, most of which have avoided being heated or modified, to other chondrites in which the material was slightly heated and somewhat altered from the form in which the first solidified. Chondrites in general offer us the best direct information about conditions and processes occurring in the earliest days of the solar nebula when planetesimals and planets were forming. Unlike the various types of chondrites, the stony meteorites called achondrites contain no chondrules and also lack volatiles. These rocks appear to have been subjected to intense heat that melted the chondrules and completely drove off the volatiles, resulting in a composition similar to Earth's basalts. The different types of meteorites evidently had a wide variety of histories. Carbonaceous chondrites are like unaltered lumps of condensed solar nebula. Achondrites seem like pieces of lava flows, whereas stony iron and iron meteorites apparently were once deep inside the molten interiors of differentiated objects. Meteorites provide evidence that a young solar system was a complicated place. A typical meteoroid has roughly the mass of a paperclip and vaporizes at an altitude of about 80 kilometers above Earth's surface. The meteor trail points back along the path of the meteoroid. So if you study the direction and speed of meteors, you can get clues to their orbits in the solar system before they encountered Earth. One way to backtrack meteor trails is to observe meteor showers. On any clear night, you can see 3 to 15 meteors per hour. But on some nights, you can see a shower of hundreds of meteors per hour that are usually obviously related to each other, seeming to come from a single area in the sky called a radiant of the shower. Meteor showers are named after the constellation from which they seem to radiate. For example, the Perseid showers, seen in mid-August, radiates from the constellation Perseus. The fact that the meteors in a shower appear to come from a single point in the sky means that the meteoroids were actually traveling through space along parallel paths. You see the fiery tracks through Earth's atmosphere in perspective, so they appear to come from a single radiant point, just as parallel railroad tracks seem to come from a single point on the horizon. So in image A, meteors in a meteor shower enters Earth's atmosphere along parallel paths, but perspective make them seem to diverge from a single point in the sky. Then in image B, similarly parallel railroad tracks appear to diverge from a point on the horizon. In image C, meteors in a shower are debris left behind as a comet icy nucleus vaporizes. The rocky and metallic bits of the matter spread along the comet's orbit. If Earth passes through such a material, you can see a meteor shower. The meteoroids in a meteor shower are understood to be dust and debris released from the icy nucleus of a comet. When Earth passes through the stream of material, you see a meteor shower. In some cases, the comet has wasted away and is no longer visible. But in other cases, the comet is still prominent, although located somewhere else along its orbit. For example, each May, Earth comes near the orbit of Comet Halley, and you can see the Eta Aquaris shower. Each October, Earth passes near the other side of the orbit of Comet Halley, and the Orionoid shower appears. Even when there's no shower, you can occasionally see meteors that are called sporadic meteors because they are not part of specific showers. Studies of the trails of sporadic meteors reveal they have a dual source. Many come from comets, as do meteors and showers, but a few come from the asteroid belt. Objects that are big and durable enough to become meteorites on the ground seem always to come from the asteroid belt. The physical characteristics of meteorites provide evidence that they are fragments of parent bodies in the asteroid belt that were large enough to grow hot from radioactive decay or other processes. They then melted and differentiated to form iron-nickel cores and rocky mantles. The molten iron cores would have been well insulated by the thick rocky mantles, so that the iron would have cooled slowly enough to produce big crystals that resulted in a Whitman statement patterns. Some stony meteorites that have been strongly heated appear instead to have come from the mantles or surfaces of such bodies. Stony iron meteorites apparently came from boundaries between stony mantles and iron cores. Collisions could break up such differentiated bodies and produce different kinds of meteorites. In contrast, chondrites are probably fragments of smaller bodies that never melted, and carbonaceous chondrites may be from unaltered bodies that formed especially far from the Sun. So here we can see the origin of meteorites. So a large planetesimal can keep its eternal heat long enough to differentiate. Collisions break up the layers of different compositions. Meteorites from near the surface are rocky. Meteorites from deeper inner planetesimals were heated to high temperatures. Fragments from near the core might have been melted entirely. Fragments of the iron core can fall to Earth as iron meteorites. Asteroids are distant objects too small to study in detail with Earth-based telescopes. Astronomers, nevertheless, have learned a surprising amount of those little worlds using spacecraft and space telescopes. Evidence from meteorites showed that the asteroids are the last remains of the rocky planetesimals that built the terrestrial planets 4.6 billion years ago. So notice 4 important points and 3 new terms. Most asteroids are irregular in shape and battered by impact cratering. Many asteroids seem to be rubble piles of broken fragments. Some asteroids are double objects or have small moons in orbit around them. This is further evidence that asteroids have suffered collisions. A few asteroids show signs of geological activity that probably happened on their surfaces when those asteroids were young. Asteroids can be classified by their albedos, colors, and spectra to reveal clues to their compositions. This also allows them to be compared to meteorites in labs on Earth. C-type, S-type, and N-type asteroids are the main classes discovered by this method. So remember, hint for the exam, C-type, S-type, N-type. The first asteroid was discovered in 1801 by the silicon monk Giuseppe Piazzi and later named Ceres. Astronomers were excited by Piazzi's discovery because Ceres orbits 2.8 AU from the Sun in a wide gap between Mars and Jupiter, where it was thought a planet ought to be. But Ceres has less than 1/4 the diameter of Earth's moon, much smaller than any of the planets. 3 even smaller objects, Pallas, Juno, and Vesta, were discovered within a few years, all orbiting between Mars and Jupiter. So astronomers decided that Ceres and the other asteroids should not be considered true planets. You learn in Chapter 18, Section 6, that Ceres, the largest object in the asteroid belt, has now been reclassified as a dwarf planet because it has enough gravitational strength to squeeze itself into a spherical shape, but not enough to have swept up or cleared away the rest of the asteroids. Today, more than 400,000 asteroids have well-charted orbits. Other than dwarf planet Ceres, only 3 are larger than 400 kilometers in diameter. Most are much smaller. There are probably 1 million or more that are larger than 1 kilometer in diameter. Astronomers are sure that all the large asteroids in the asteroid belt have been discovered, but are also sure that many small asteroids remain undiscovered. Movies and TV have created a common misconception that flying through an asteroid belt is a hair-raising plunge, requiring constant dodging left and right. The asteroid belt between Mars and Jupiter is actually mostly empty space. In fact, if we were standing on an asteroid, it would be many months or years between sightings of another asteroid. You don't have to go all the way to the asteroid belt if you want to visit an asteroid. Some follow orbits that cross the orbit of the terrestrial planets and come near Earth. Others wander far away among the Jovian worlds. There are also asteroids that share orbits with the planets. Several research teams are now intent on identifying near-Earth objects, so NEOs, which could potentially hit Earth. The most dangerous type of NEOs, those with orbits that cross Earth's orbit, are called Apollo orbits, of the first such asteroid discovered. The combined searches are estimated to have found at least 93% of the Apollos and other NEOs larger than 1 kilometer in diameter, and are now focused on finding a similar percentage of objects down to a size of about 150 meters. In March 2009, NEO searchers spotted a small asteroid 2 to 3 meters in diameter, about the size of a small truck, on a collision course with Earth. Astronomers were able to observe it in a space before impact and discovered that its color and albedo match a type of asteroid found mostly in the outer belt. The asteroid entered Earth's atmosphere over the deserts of northern Sudan and exploded. Scientists from the United States and Sudan searched for pieces of the object. So in this image, we can see a diagram plots the position of known asteroids between Sun and the orbit of Jupiter on a specific day. Most asteroids are in the main belt. Squares filled or empty show the location of known comets, although asteroids and comets are small bodies and lie far apart. There are a great many of them in the inner solar system. So let's have a little bit of a discussion. Why is it important to track these NEOs? Yes, Mr. Visage.
I have this. I think it's because it might at some point crash into Earth, maybe.
Yes. So, for example, if we have a asteroid bigger than 1 kilometer, that will survive, definitely survive, entering Earth's atmosphere. if that hits a city, it will have enough power to flatten the entire city. So we can, yes, exactly, to identify which put Earth in danger. But that raises another question. How do we protect ourselves from these asteroids? Yes, Mr. Visagie.
So I've had an idea where we'd probably have to shoot rockets that has a big radius.
Yes, so that's one of the possible solutions. So yes, so if we can calculate where they are, we can do mass evacuation. But if the asteroid is made out of a not a dense material, then we could just send up a few missiles and basically vaporize it. Yes, Mr. Leguillon.
So since some of these meteors and asteroids are made out of iron, so could we not just use a magnet to sort of redirect them?
Yes, that is actually one of the proposed ideas. So there's a few proposed ideas. So one of the ideas is if they are made of a material that is not dense, then we can vaporize them. But the problem is if it's a big asteroid with dense materials such as iron, and you bombard it with rockets, then there's a possibility that you might break it into smaller pieces. And then you will have multiple asteroid hits on Earth that will cause even more damage. So the idea is, if it is, yes, Mr. Visagie.
So this is not really scientific, but what if we could calculate where the trajectory is going to hit Earth and then evacuate those areas so that we don't lose human life?
Yes, that is what's supposed to happen, but think about the economic and natural disasters. So think about let's take a stupid example. An asteroid is heading for South Africa and it will cause damage the size of the entire Gauteng. So that is a lot of damage. So what you would rather do is, yes, you evacuate the entire Gauteng to keep loss of life as small as possible, but rather we would need to find ways to alter the path of the asteroid so it misses Earth. So that could be by sending a spacecraft that lands on the asteroid and fires up rockets to push it out of the way. That could be sending spacecraft to it with giant electromagnetic magnets to push it out of the way. And this is one of the duties of the planetary protection officers as well, is to come up with these contingency plans. And that is why it's important for us to track these NEOs.
So is it possible to attach rockets on these asteroids? So do you know how what are these things called? So you see when jets land on like these ships, so on yes sir, these ships on the ocean, and then like the jets go in and land on there, and then like sometimes the parachute comes out.
Yes.
So can't you like sort of like shoot, like, I mean not shoot, but like can't you like sort of attach like a parachute onto the asteroid, and then as it enters the Earth's atmosphere it sort of slows it down?
So unfortunately, remember though, when it enters the atmosphere, these asteroids usually travel around Mach 15, so that means 15 times faster than the speed of sound. So if you touch an asteroid on it, it will just purely rip off. So when you deploy a parachute, the parachute only becomes effective when you are not supersonic anymore. So if you look at these rocket launches as well, so for example, when a crew capsule returns from the International Space Station, when it enters the atmosphere, you will have a small drogue chute deploying just to slow down a little bit before the main chute deploys, otherwise it will be ripped right off. But unfortunately, these asteroids are moving too fast for parachutes to use. So the best course of defense will be to deflect or adjust the path of these asteroids. Yes, Mr. Visagie.
So if I'm understanding with the rockets, what you're saying is that we send the rockets while the asteroids are in orbit or in the orbital zone. It hasn't exactly hit the Earth's atmosphere yet.
Yes, so you want to do so, try to have a rocket rendezvous with the asteroids long before it reaches Earth. So even if you nudge the asteroid's trajectory by 1 or 2 degrees, that will be enough in the long run so it misses Earth. So if the asteroid is closer to Earth, that means you will need more power to make that angle change larger. But if you can intercept it much sooner, then you only have to change the orbit by a few degrees.
So why can't we just track the asteroids, and then if it reaches a certain region of space around the Earth, then we start looking at how we can deflect it before it gets anywhere closer?
Yes, that is exactly what we are doing. So Seacom about won't it be another million years before an asteroid the same size as the one that took out the dinosaurs? So if you look at peer statistics, we are overdue for a mass extinction event. So continuing, search team leader on the left of the Faculty of Physics and Science at the University of Cornell and meteor astronomer Peter Jeniskens of the Carl Sagan Center at SETI Institute proposed with one of the first fragments found in a small asteroid that exploded over the Sudanese desert in March 2009. They found about 4 kilograms of fragments corresponding to a rare type of stony meteorite. For the first time, a definite connection could be made between an asteroid observed in space and meteorites with properties measured in Earth laboratories. In 2010, the Japanese probe Hayabusa returned a capsule to Earth containing a few tiny grains from the surface of the S-type asteroid Itokawa, which were found to be chemically identical to one of the most common types of ordinary chondrite meteorites. There are other non-belt asteroids beyond the main belt. Gravitational effects of Jupiter and the Sun combine to trap two groups of asteroids in Lagrange points that are 6 degrees ahead and 6 degrees behind the planet in its orbit. These are called Trojan asteroids because individual objects have been named after heroes of the Trojan War. Astronomers have also found a few objects in Lagrange points of the orbits of Mars and Neptune. The object Churin, found in 1977, is about 170 kilometers in diameter. Its orbit carries it from the orbit of Uranus to just outside the orbit of Saturn. Objects like Churin, with orbits between or crossing orbits of the Jovian planets, are called centaurs. Although it was first classified as an asteroid, Churin later surprised astronomers by suddenly releasing jets of vapor and dust. You will learn in the next section that this more resembles the characteristics of comets than asteroids. Centaurs show that the distinction between asteroids and comets is not clear-cut. As technology allows astronomers to detect smaller and more distant objects, they are learning that our solar system contains large numbers of these small bodies. The challenge is to explain their origin. An old hypothesis proposed that asteroids are the remains of a planet that exploded. Planet-shattering death rays make for exciting science fiction movie, but in reality planets do not explode. The gravitational field of a planet holds the mass together so tightly that completely disturbing the planet would take tremendous energy. In addition, the present-day total mass of asteroids is located only about 1 to 20 the mass of Earth's moon. Hardly enough to be the remains of a planet. So look back to the figure that opens at chapter 15 to see extrasolar planetary system with asteroid belt interior to the orbit of the Jovian planet. The arrangement may have the same cause as in our own solar system. Astronomers have evidence that asteroids are the remains of material laying 2 to 4 AU from the Sun that was unable to form a planet because of the gravitational influence of Jupiter. The next planet outward, so over the 4.6 billion year history of the solar system, most of the objects originally in an asteroid belt have collided, fragmented and been covered with craters. Some asteroids were perturbed by gravity of Jupiter and other planets into orbits that collide with planets or the Sun, caused them to captured as planetary satellites or ejected from the solar system. The present-day asteroids are understood to be a very minor remnant of the original mass in that zone. Even though most of the planetesimals originally in the main belt have been lost or destroyed, the objects left behind carry clues to their origin and their albedos and spectroscopic colors. For example, C-type asteroids have albedos less than 0.06 and look very dark to your eyes. They are probably made of carbon-rich material similar to that in carbonaceous chondrite meteorites. C-type asteroids are more common in our outer asteroid belt. It is cooler there, and the condensation sequence predicts that carbonaceous material would form there more easily than in the inner belt. The second largest asteroid, Vesta, has solidified silicate lava on its surface. Ceres, 950 kilometers in diameter, almost twice as big as Vesta, but is surface is ice-rich carbonaceous material. Herschel Space Telescope observations of Ceres reveal water vapor venting from two regions on its surface. The Dawn spacecraft arrived at Ceres in 2015, imaging occasional haze in a large crater that may be one of the water vapor sources. The differences between the two largest asteroids offer a real puzzle of planetary scientists. In image A, the image of the asteroid Vesta made from a distance of 2,700 kilometers by NASA's Dawn spacecraft show Vesta's south polar region, which is dominated by impact basin. In image B, dwarf planet Ceres, the largest object in the asteroid belt between Mars and Jupiter, the prominent white spots may be salt deposits left by evaporating water. Although there are still mysteries to solve, you can understand the story of asteroids. They are fragments of planetesimals, some of which differentiated, developed molten metal cores, in a few cases even had lava flows on their surfaces, and then cooled slowly. The largest asteroids astronomers see today may be nearly unbroken examples of original planetesimals, but the smaller asteroids are fragments produced by 4.6 billion years of collisions. So before starting with comments, another discussion point for you guys. I don't know if you realized it, but something that's going to happen in the near future is asteroid mining. A lot of the biggest mining companies in the world now has researchers working for them to try and find a way to do asteroid mining. Because we know these asteroids formed in the planetary nebula around the Sun, and that means some of these asteroids has already been identified by looking at spectroscopic observations that they are mineral rich and also rich of metals. So some of these asteroids have very high concentration of iron, gold, silver, nickel, platinum. So if you were able to go to the asteroid and mine it, or even go to the asteroid, hook it to some system, bring it back to Earth, there is an tremendous amount of money to be made from it. But the problem arises is, how do you get to the asteroid and how do you get the material back? So there are now some proposals by mining companies to send more probes to these asteroids and then later on put up mining bases on these asteroids to be able to do mining and then send the material back to Earth. Yes, Mr. Levuyo.
So if I remember properly, so you said we have an asteroid belt right after Mars, right?
Yes.
So wouldn't would it not be more cost effective if we we had a base on Mars, and then we mine from there, like for example, like we transport probes to that asteroid belt and then bring it back to Mars, and then like once, I think it's once every 2 years, like we Earth and Mars get close to one another, and then it makes traveling to the other planet much cheaper, right?
Yes. So that is one of the, you're correct, Mr. Levure. That is one of the proposals going around. So that's one of the proposals. Some of the other proposals is that we have a space station at the asteroid belt. So we can send spacecraft to the space station, they rendezvous at the space station, dock, and then from there on go to the different asteroids. Or the other idea is that we are on the larger asteroids, that we have a base on the asteroid. So you send up a spacecraft, it travels to the asteroid, it lands on the asteroid, and then you have crew can unload crews or even robots. You mine the asteroid, the material is taken back to the spacecraft, it gets launched again, it flies back to either Mars, the Moon, or Earth, lands again, and offload this material.
And so, why aren't they like so? Why have we not tried to mine the moon?
So that is something that is also coming up. But if we do spectroscopic observations of the moon, we know the moon is not rich in precious metals. So on the moon, we basically, if we compare it bluntly, it would be just as ordinary rock we find here on Earth. So it's not worthwhile to moon the Earth because we're not getting something valuable from the moon. But if you look at spectroscopic observations, I'm not completely sure about the statistics, but in the asteroid belt, they have located a asteroid that consists out of, I think, about 70%, either it's either 70% silver or 70% platinum, either one of the two. But it's estimated that the net worth of that asteroid is something ridiculous like $30 trillion. So that brings us to another point. If you get to the asteroid, you bring it back, and you have $30 trillion worth, what would that do to the economy, and what will that do to the value of that material being mined?
But then, so correct me if I'm wrong. So, but then, like in order, like for example, so say oil. So, one way we
Yes,
find out where oil deposits are from seismic activities, right? So, for example, like if there's like an earthquake from, if I'm not sure, but like it has to do something with sound, where you can find um um whether there's an oil deposit there. So when it comes to the moon, how do we know that like it's just rock under it? Like there's no thing like oil or
I understand
like.
what you're saying. So usually, I don't know exactly how they determine where oil deposits are, but it is making, if I'm maybe completely wrong, but as far as I understand, they make use of some sort of um, sonar to determine it. But by using radar and spectroscopic evidence, we know what is on the surface of the moon, and we can calculate the density of the moon, calculating what it should be. So there may be some deposits of something, but not worthwhile. But where in the asteroids, we definitely know what its composition is, and therefore know it is, we can mine it. So, Senior from Mr. Van der Berg, so yes, if you have a lot of that material, the supply and demand will become cheaper. So that is something else that might happen as well. But that is why these mining companies are investigating the possibility of asteroid mining. And that will happen sooner than you guys realize. So some of the best estimates of these mining companies suggests they want to start mining these asteroids in the next 15 years.
So then, so correct me if I'm wrong. So, but then, like in this course, so we didn't necessarily go into like, so you saying like through what was it? Spectroscopy
Yes.
is how we can find out the density of these things. So then, so you saying that through light. So for example, not radio waves. Is it radio waves or X-rays? X-rays and like all these shorter wavelengths. So they would penetrate through the outer crust and then go into the center. And then because we know that the center of the moon is denser, then we can like observe the like what's in the core of the moon in that way.
So, not really. So what we do is discussed in one of the earlier chapters with spectroscopic observations. We look at all wavelengths. So that means from radio waves all the way up to gamma rays. And we know gamma rays and X-rays can penetrate most solid matter. The only material that can stop basically or absorb X-rays and gamma rays are lead and silver, gold. But by looking at all these frequencies, so looking at the entire spectrum, we know certain materials and elements radiate certain frequencies, so that means emission spectrums. And we know certain elements absorb certain frequencies that have absorption spectrums. And we know what the emission absorption spectrums are of all known elements. So therefore, we can determine what the chemical composition is of these bodies that we are observing.
Yes, sir. So, but then, like, my question is, how do you observe what is inside when the light doesn't necessarily penetrate through? Because if you're saying that
So light won't penetrate through, but X-rays will penetrate through. Gamma rays will penetrate through.
So then, so basically, like the same thing as visible light, you'll sort of see specific elements give out specific absorption lines. Is that the same thing with the X-rays and the gamma rays?
Yes, exactly.
And then from that, okay. So then that's basically how you determine what the core is made out of.
Yes.
Oh, okay, makes sense. Thank you, sir.
Pleasure. Mr. Groenewald, I think you are correct. So it is a form of ultrasound. So if you're in your free time, you can Google asteroid mining and you will see a lot of articles published on it. So now we're going to start looking at comets. Yes, Mr. Levuyo.
Sorry, sir, before we move on from the mining, sir. So I also heard that there's also plans on mining gases from gas giants as well.
Yes, that is something that hasn't been spoken about a lot in the astronomy community, especially because it's so difficult to get to the Jovian worlds. But the idea is that you put a space station around one of those Jovian worlds, that is possible, and then you have spacecraft going into the upper atmosphere of those worlds, or even probes going in a little bit deeper, collecting these gases, bringing them back to the space station, and from the space station back to Earth. But so if you don't know if you guys are familiar with the series The Expanse, a great sci-fi series, and that is one of the things they do in that sci-fi series. And if you are Star Wars fans, if you are familiar or recognize Cloud City, that is a flying city in the atmosphere of Bespin, that is what a city in Star Wars makes the living on. They mine the gases in the atmosphere.
And so would it be possible in some way that we can also create some type of city that floats in and like above an atmosphere.
Yes, so it's a bit far-fetched and only science fiction at the moment, but yes, if we develop the technology to do it, then why not?
Thank you, sir.
Pleasure. So now we're going to start looking at comets. So few sights in astronomy are more beautiful than a bright comet hanging in the sky. It is a common misconception that comets whiz rapidly across the sky like meteors. Actually, a comet's motion is hardly apparent. Night by night, its position shifts slightly against the background stars. It may remain visible for months. While everyone can enjoy the beauty of comets, astronomers study them because they are messengers from the past carrying cargoes of information about the origin of the solar system. So in this image, we can see Comet McNaughty swept through the inner solar system in 2007. It was a dramatic sight in the southern sky. Seen here from Australia, the comet was on its way back to deep space after making its closest approach to the Sun 10 days earlier. Comet McNaughty began its passage with a period of about 300,000 years. But gravitational perturbations by the planets changed its orbit shape from elliptical to hyperbolic, so it will never return, but instead is leaving the solar system to journey forever in interstellar space. As always, you should begin the study of a new kind of object by summarizing its observational properties. What do comets look like, and how do they behave? Notice 3 important properties of comets plus 3 new terms. Comets have 2 kinds of tails, shaped by the solar wind and solar radiation. Gas and dust released by a comet's icy nucleus produces a head or coma, and are then blown outward away from the Sun. The gas produces a gas tail, and the dust produces a separate dust tail. Comet dust produces not only one of 2 types of comet tails, but also spreads through the solar system. Some of those comet dust particles later encounter the Earth and are seen as meteors. Evidence shows that some comet nuclei are fragile and can break into pieces. The nuclei of comets are quite small and cannot be studied in detail using Earth-based telescopes. Nevertheless, when a comet nucleus approaches the Sun, it emits material that forms into a coma, so the head and the tail that can be millions of kilometers in size and easily observed. Spectra of a comet, or comae, the plural of it, and tails indicate the nuclei must contain ices of water and other volatile compounds such as carbon dioxide, carbon monoxide, methane, ammonia, and so on. These are the kinds of compounds that would have condensed in cold regions of the solar nebula. This convinces astronomers that comets are ancient samples of the gases and dust from which the outer planets formed. As the ices absorb energy from sunlight, they sublime, change from a solid directly into a gas. The gases break down and also combine chemically, producing other substances found in comet spectra. For example, vast clouds of hydrogen gas observed around the heads of comets are understood to derive from breakup of ice molecules. 5 spacecraft flew past the nucleus of Comet Halley when it visited the inner solar system in 1985 and 1986. Other spacecraft flew past the nuclei of Comet Borley in 2001, Comet Wild 2 in 2004, and Comet Tempel 1 in 2005, and Comet Hartley in 2010. Images show that all these comet nuclei are 1 to 10 kilometers across, similar in size to many asteroids and also irregular shape. In general, these nuclei are darker than a lump of coal, which suggests composition similar to carbon-rich carbonaceous chondrite meteorites described earlier in this chapter. The mass and density of comet nuclei can be calculated from a gravitational influence on passing spacecraft. Comet nuclei appear to have densities between 0.1 and 0.25 grams per cubic centimeter, much less than the density of ice. Also, as you will learn later in this chapter, comets subjected to tidal stresses from Jupiter or the Sun come apart very easily. Comet nuclei have been described as dirty snowballs or icy mudballs, but it seems to be incorrect. Their shapes, low densities, and lack of material strength suggest that comets are not solid objects. The evidence leads astronomers to conclude that most comet nuclei must be fluffy mixtures of ices and dust with significant amounts of empty space. On the other hand, images of the nucleus of Comet Wild 2 revealed cliffs, pinnacles, and other features that show the material has enough strength to stand against the weak gravity of the comet. So here we can see visual wavelength images made by Hubble Space Telescope and from passing spacecraft show how the nuclear comets produce jets of gases, regions where sunlight vaporizes ices. So here we can see the nucleus of Comet Halley is irregular in emitting jets from active regions. Here we can see HST image of Comet Hale-Bopp. The nucleus of Comet Wild 2 is highly irregular. Nucleus of Comet Hartley 2. You can see active regions on a nucleus of Comet Borrelly emits jets. The nucleus of Comet Churyumov, oh, how do you pronounce that? I have no idea. The mass and density of comet nuclei can be calculated from their gravitational influence on passing spacecraft. Comet nuclei, we have done this slide. Sorry, this is a copy of a mistake I made. So the nuclei of comets appear to have a crust of rocky dust left behind as the ices vaporize, breaks in the crust and expose ices to sunlight. And vents can occur in those regions. It also seems that some comets have large pockets of volatiles buried below the crust. When one of those pockets is exposed and begins to vaporize, the comet can suffer dramatic outbursts, as Comet Holmes did in 2007. So do you know what the current status of Hubble is? So Hubble is currently in a weird state because the primary computer failed and they can't get the primary computer online. The secondary computer is supposed to take over in such an event, but seems like there are weird stuff happening with the secondary computer as well. So the secondary computer, for some reason, the last thing I have heard about it, is the secondary computer boots up, it takes control, then Hubble operates for a couple of minutes, and then for some weird reason, the secondary computer reboots itself. So ideally, it would be if they're going to try and see if they can sort out the computer remotely, ideally it would be to send a manned mission to Hubble to repair it or do a computer swap out, but I don't know if such a mission will be approved. The Stardust spacecraft flew through Comet Wild's tail in 2004, collected dust ejected from a comet's nucleus, and returned samples to Earth for analysis. In 2005, Deep Impact released a probe that collided with Comet Tempel 1 at 10 kilometers. The probe broke through the comet's crust and blasted vapor and dust into space, allowing Deep Impact Plus space telescopes and observatories on Earth to analyze it. Stardust and Deep Impact data revealed the surprising fact that some dust is crystalline, must have formed originally in warm locations near the Sun, but then somehow was included in comet nuclei in a cold outer solar system. So, bit off topic, have you guys ever watched the movie Deep Impact? It's a 80s sci-fi movie. I think Bruce Willis is one of the guys playing one of the lead roles. It's an asteroid on a collision path to Earth and needs to be destroyed by nuclear devices. So it's a very good movie if you are a sci-fi fan. It is deep impact. Pleasure. So the Rosetta spacecraft that you guys still probably remember began orbiting the nucleus of comet so I have no idea how to pronounce that word, but I assume it's Russian, in 2014, dropping a probe, Philae, which landed and returned data and images from the surface. Rosetta and Philae detected organic molecules such as methanol and formaldehyde emanating from the comet's surface. So here we can see image from the Rosetta spacecraft and the lander Philae on the surface of the asteroid. So what is the origin and history of these comets? Family relationships among the comets can give you clues to their origin. Most comets have long elliptical orbits with periods greater than 200 years and are known as long period comets. The long period comet orbits are randomly inclined to the plane of the solar system. So those comets approach the inner solar system from all directions. Long period comets revolve around the Sun in about equal numbers in prograde orbits, so meaning the same direction in which the planets move, and retrograde orbits. In contrast, about 100 or so of the 600 well-studied comets have orbits with periods less than 200 years. These short period comets usually follow orbits that lie within 30 degrees of the plane of the solar system, and most revolve around the Sun prograde. Comet Halley, with a period of 76 years, is an unusual short period comet with a retrograde orbit. A comet cannot survive long in an orbit that brings it into the inner solar system. The heat of the Sun vaporizes millions of tons of ices during each passage and reduces comets to inactive bodies of rock and dust. Such comets can last at most 100 to 1,000 orbits around the Sun. Astronomers calculated even before a comet completely vaporizes from solar heating, it can't survive more than about 500,000 years crossing the orbits of the planets, especially Jupiter, without having its path rerouted into the Sun or out of the solar system or colliding with one of the planets. Therefore, comets visible in our skies now can't have survived in their present orbits for 4.6 billion years since the formation of the solar system, and that means there must be a continuous supply of new comets. So where do they come from? In the 1950s, astronomer Jan Oort proposed that long-period comets are objects that fall inward from what has become known as the Oort cloud, a spherical cloud of icy bodies that extend from about 10,000 to 100,000 AU from the Sun. Astronomers hypothesized that the Oort cloud objects were originally planetesimals formed in the outer solar system that were tossed to their current distant locations by the gravitational influences of the growing Jovian planets. The Oort cloud is estimated to contain several trillion icy bodies, far from the Sun. They are very cold lac and tails and are invisible from Earth. Astronomers calculate some Oort cloud objects can be perturbed by the gravitational influence of passing stars so that they fall into the inner solar system. There, the heat of the Sun warms their ices and transforms them into comets. The fact that long-period comets are observed to fall inward from all directions is explained by the Oort cloud reservoir being spherical distributed around the Sun and inner solar system. So we have discussed in the formation of galaxy and galaxy evolution that galaxies collide into one another and cannibalize each other. So when we look at galaxy collisions, this individual stars in the galaxy will be very rare if two stars collide with one another. But while this collision of galaxies is happening, what is actually happening more is the Oort clouds of these different stars interact with one another. So these objects in the Oort clouds will collide with one another. So a few short period comets, including Comet Halley, also seem to have originated as long period comets from the Oort cloud, but then had their orbits altered by a close encounter with Jupiter. However, that process can't explain all of the short period comets. The Kuiper belt, which you first encountered in chapter 15, section 2, when you initially survey the solar system, is another source of icy bodies passing through the inner solar system. Kuiper belt objects, KBOs, orbit in the same direction as the planets and in a plane of the solar system. Mathematical models show that it's likely for KBOs, perturbed inward by influence of the giant planets, to move into an orbit resembling those of the short period comets. Comets vary in brightness and orbit. Nevertheless, there are two basic types of comets in our solar system. Some originate in the Oort cloud, far from the Sun. Others come from the Kuiper belt, just beyond Neptune. They all share one characteristic. They are ancient icy bodies that were born when the solar system was young. So now we're going to look at asteroid and comet impacts. Most meteors are small particles ranging from a few centimeters down to microscopic dust. Astronomers estimate that Earth gains about 40,000 tons of mass per year from meteorites of all sizes. That may seem like a lot, but is less than 100,000th of a trillionth of Earth's total mass. Statistical calculations indicate that a meteorite large enough to cause some damage, like the one that hit Miss Hodges and a house in 1954, strikes a building somewhere in the world about once every 16 months. Declassified data from military satellites show that Earth is hit about once a week by meter-sized meteorites. What happens when even a larger solar system object collides with Earth? Barrington Crater near Flagstaff, Arizona is 1.2 kilometers in diameter and 170 meters deep. Eugene Schumacher provides in his 1963 doctoral thesis that the crater must be the result of an impact rather than a volcanic eruption, because quartz crystals in and around has been subjected to pressure much higher than can be produced by a volcano. Further studies shown that Barringer Crater was created approximately 50,000 years ago by a meteorite estimated to have been about 50 meters in diameter, as large as a good-sized building. That hit a speed of 11 kilometers per second, releasing as much energy as a large thermonuclear bomb. An object of that size would be called either a large meteorite or a small asteroid. Debris at the site shows that the impactor was composed of iron. So here we can see an image A. The Barringer meteorite crater is nearly a mile in diameter and was formed 50,000 years ago by impact of an iron meteorite estimated to have been roughly 50 meters in diameter. So notice the raised and deformed rock layers all around the crater. The brick museum building visible on the far rim at the right provides some idea to scale. Then in image B, like all large impact features, the Barringer meteorite crater has a raised rim and scattered ejecta. So do you guys know what is the most prominent impact crater in South Africa? Yes, you are correct. That is the Vredefort Koepel. Is the Vredefort Koepel. So Kimberley is not an asteroid strike. Kimberley is a open groove mine, as far as I'm correct. But the Vredefort Koepel is a large one, and there's just north of Pretoria, there's also a big impact crater. The Vredefort Koepel, I am not exactly on the age. But if you look at Google Maps images, you can clearly see it's an asteroid strike. And just north of Pretoria, there's also another impact crater that is quite large. I know some people, well, the astronomy club I'm part of, last year wanted to organize a hike through the impact crater just north of Pretoria. But unfortunately for that, that has become quite dangerous and quite a hot spot for muggings. So they suggest if you want to go hike through the crater just north of Pretoria, you do it in a fairly large group. On a summer morning in 1908, reindeer herders and homesteaders in central Siberia were startled to see a brilliant blue-white fireball brighter than the sun streak across the sky. Still descending, it exploded with a blinding flash and an intense pulse of heat. The blast was heard up to 1,000 kilometers away, and resulting air pressure circled Earth twice. When members of the scientific expedition arrived at a site in 1927, they found that a blast occurred above the stony Tunguska River Valley and had knocked down trees pointing away from the center of a region about 30 kilometers in radius. So 1908 Tunguska event in Siberia destroyed an area the size of a large city. Yet the area of destruction is superimposed on a map of Washington, D.C., and its surrounding beltway. In the central area, trees were burned. In the outer area, trees were blown down in a pattern away from the path of the impactor. No crater has been found at the Tunguska site, so it seems that an explosion estimated to have equal 12 megatons of TNT occurred at least a few kilometers above the ground. A detailed analysis of the available evidence suggests that the impactor's speed and direction resembles the orbits of Apollo objects. Astronomers produced computer models of objects entered Earth's atmosphere and concluded that most likely candidate for the Tunguska object is a stony asteroid about 30 meters in diameter, perhaps 1/10 the mass of the Barringer impactor. An object of this size and material strength would have fragmented and exploded at just above the right height to produce the observed blast. This conclusion is consistent with modern studies of the Tunguska area, showing that 1,000 of tons of powdered material with a composition resembling carbonish chondrites that scattered in soil. So thinking this is a 30-meter asteroid. So that's 30 meters. So imagine what would happen to Earth if a bigger one hit Earth. There are some very big craters in the solar system, for example on the Moon, that show what can happen when full-sized asteroid of comet collides with a planet. Also, Earthlings watched in awe in 1994 as fragments from nucleus of comet Schumacher-Levy slammed into Jupiter with a series of explosions equaling millions of megatons of TNT. The impacts left scars larger than Earth visible on Jupiter's cloud tops for months afterwards. In 2009, another object, it was not observed prior to the impact, left a single blemish on Jupiter that was easily observed from Earth. Evidently, impacts large enough to significantly affect a giant planet like Jupiter happen impressively often. So that's why Jupiter protects us from these asteroids. So here we can see in 1992, comet Schumacher-Levy 9 passed within 1.3 planetary radar of Jupiter's center, well within its rush limit, and tidal forces ripped the nucleus into more than 20 pieces. The fragmented pieces were as large as a few kilometers in diameter and spread into the long string of objects that looped away from Jupiter and then fell to strike the planet, producing massive impacts over a period of 6 days in July 1994. Note that the impact flash in the upper right panel is larger than Earth. So here we can see the damage. So here we can see only 9 minutes after one impact, the fireball was brilliant in the infrared. So here we can see infrared spots where Jupiter was hit. What would happen if an object the size of Schumacher-Levy 9 or even larger were to hit Earth? 65 million years ago, at the end of the Cretaceous period, over 75% of the species on Earth, including the dinosaurs, became extinct. Scientists have found a thin layer of clay all over the world that was laid down at that time. And It is rich in the element iridium, common in meteorites but rare in Earth's crust. This suggests that an impact occurred that was large enough to have altered Earth's climate and caused a worldwide extinction. So see a comment. Sir, I'm just curious, and this is sort of unrelated to the topic, but can we calculate how far the gravitational influence of a body extends? Yes, we can. That is just a, if you make use of Kepler's laws and a bit of classical mechanics, yes, we can calculate how far the influence extends. Geologists have located a crater at least 180 kilometers in diameter centered near the village of Chicxulub in northern Yucatan region of Mexico. Although the crater is now completely covered by sediments, mineral samples show that it contains shock quartz typical of impact sites and that it has the right age. The impact of an object 10 to 15 kilometers in diameter formed the crater about 65 million years ago, just when the dinosaurs and many other species died out. Most scientists now conclude that this is the scar of the impact that ended the Cretaceous period. So in image A, the giant impact scar buried in Earth's crust near the village of, how do you pronounce that again, of Chicxulub, in the northern Yucatan Peninsula was formed about 65 million years ago by impact of large asteroid or comet. Then image B. This gravity map shows the extent of the crater and surrounding region of the disturbed crust hidden below limestone deposited long after the impact. There are a number of major extinctions in the fossil record, and at least some of these were probably caused by large impacts. Large asteroid impacts on Earth happen very rarely from a human perspective, but they happen often relative to geological and astronomical time scales. For example, astronomers estimate an Apollo object hits Earth once every 250,000 years on average. A typical Apollo with a diameter of 1 kilometer would strike with the power of a 100,000 megaton bomb and dig a crater more than 10 kilometers diameter. Astronomers estimate that there are about 1,000 Apollos 1 kilometer in size or larger, and the good news is that none of them are known to be on track to hit Earth in the foreseeable future. The bad news is that not all of these dangerous Apollo objects have been found yet. A significant danger lies in the more common smaller yet still substantial meteorites, which are difficult to detect with current telescopes. For example, an asteroid designated 367943 Duende, estimated to have been 30 meters in diameter, about the same size as the Tunguska impact that passed only 27,700 kilometers from Earth's surface in February 2013. That is closer than humanity's geosynchronous communications and weather satellites. A very near miss indeed, yet it was discovered only a year earlier. The future of our civilization on Earth may depend on our doing an increasingly careful job of tracking both large and small objects that cross our path with surprising frequency. And that, ladies and gentlemen, concludes our chapter of the solar system. So we only have one lecture left, and that will be on extraterrestrial life. So when it comes to gravitational influence, it is sort of like a trend. The most massive object necessarily have bigger gravitational influence, or is it all about density? Do denser objects have greater radius of gravitational influence? So it all depends on not density, we can say density, but it all depends on mass. So the more mass an object have, the larger gravitational influence it will have, and the more mass, the further it will can extend. So I haven't looked at the timetable yet. So my planning was that we do the last lecture next week, Monday. But last night lecture, you guys informed us that the next week, Monday, we are following a Wednesday timetable, if I'm not mistaken. And what is happening on Tuesday? So that's weird. So why? So let me just open up the UP calendar on my side. Just want to check what's going on. Okay, so I have the UP calendar open. So UP calendar. Okay, so here we have when is the 5th of July? Wednesday timetable is followed. So let me just open up my calendar. The 5th of July is Monday. And then exam starts on the 7th. So that is the Wednesday. So I will send out an announcement. So it won't be a compulsory lecture, but we'll still be examined on it. But would you guys vote that we have our last lecture on next week, Tuesday evening? Yes, Mr. Visagi.
So I was just wondering if we're gonna have the lecture on Tuesday, would it be at all possible to maybe schedule it to be a little bit earlier because a lot of us are writing COS 151 on the Wednesday.
Okay, so so if you're running an exam on a Wednesday, we can even make the class on a Wednesday as well.
I think that would be preferred.
For Wednesday.
Yes.
Okay, but I will create a poll for the entire class, but let's schedule it then for next week, Wednesday. What time do you prefer?
I'm just quickly having a look at what time the exam starts, but I think it starts at 8 o'clock and then finishes midday.
Okay, so while I have you guys here, there's a few admins. So this is one thing we need to decide on. So which date you would like to have our last class. So it looks like I messed up my planning a little bit for Monday following a Wednesday timetable. So, okay, so I don't actually know what time the exam is. So if we say Wednesday evening again at 5:30, next week Wednesday 5:30. Okay, so let's schedule it for next week at 5:30 again for our last chapter. Then two other things I want to know about. So in the unfortunately, I have to be in the exam period somewhere, but you guys can pick the date and time. I want one. We can break this. I want to schedule one session where we can go through the memos of the semester test, the SIG test, and I will also go through the memo of the mock July, after mock exam. So yes, 7 July, 5:30.
So for that one, I was wondering if we could maybe also do it next week, maybe on the Friday or Saturday, if there's no other exam sections for any other modules.
It all depends on the class. So I go with the democratic vote. So what the majority of the class wants, then I will schedule. Okay, so you guys say next week Friday. So what time next week Friday? Okay, so Friday is one possible option. So do you guys have another possible date we can look at? We can even do it the Saturday the 10th after the exam. We can do it Thursday as well. So do you want to poll up now in this live session, or can I send out a Google poll later this evening? Okay, I'll send a poll out and I'll get back to you on that. And then one last thing I want to schedule that's also not compulsory but will help you. The night before our exam, let's say from 5 p.m. to 7 p.m., I will have an open session if you have questions for the exam and something you need help with. Cool. So one thing we can do is for the lecture before the exam, we can use that also to go through the memos if you want to, but we can schedule that on a different date as well.
So to be clear, so our exam is, the scope of the exam is everything we covered this year, this semester.
Yes.
Okay, thank you, sir.
Pleasure.
So we'll also have 50 multiple choice questions in this exam.
So this exam, the format is going to be a little bit different, but you'll see it in the mock exam I will give to you guys. So 70% of the questions will be multiple choice, 20% will be short answers, and then there will be one question that is a long question. And I think this is, I still need to set the paper. I think the exam is 2 or 2.5 hours. It's a pleasure. Then I will see you all next week, Wednesday, for our last class, for last lecture. So the last lecture may be a little bit silly because we are going to speak about extraterrestrial life and what that will mean to humanity if we discover extraterrestrial life. Because if you look at it, that will cause a major shift in people's belief and how they see the universe, but that is something we'll discuss in next week's class. So have a great week. Good luck with finishing up the last of your modules. I hope your semester tests, your semester marks will be great. I will have the assignments marked by Friday, then I will release the marks. Then I will calculate your semester marks. Then the HOD just needs to approve the semester marks. But that will most likely be released also next week somewhere, or and latest the week after that. So I'm now going to stop the recording. So have a great week, everyone.